Cosmic inflation is the theory that in the very first moments of the universe's existence, it underwent a rapid expansion, exponentially increasing in size in fractions of a second. This colossal inflation occurred within the first tiny fractions of a second after the Big Bang. This concept helps explain a number of puzzling observations in cosmology, such as the homogeneity of the cosmic microwave background radiation and the large-scale structure of the universe. Simply put, inflation suggests that although the universe started out extremely small, it expanded rapidly, flattening the distribution of energy and creating the conditions for galaxies and stars to form. The theory of inflation was formulated in the early 1980s by cosmologist Alan Guth. His pioneering work suggested that during the formative period, the universe expanded much faster than the speed of light, under the influence of the high-energy field that dominated the cosmos at the time. Guth's idea provided a convincing explanation for the isotropy and homogeneity observed in the universe, and solved problems such as the flatness problem associated with the curvature of space. Following Alan Guth, other theoretical physicists have developed his work. Notable figures such as Andre Linder and Paul Steinberg contributed variations on the inflationary model, making it a well-developed basis for cosmology. Their contributions included various scenarios and mechanisms that could have led to inflation, further enriching our understanding of the early moments of the universe. This theory not only provides a glimpse of how things started, but also suggests that inflation may still be occurring now, albeit at a much slower pace. Understanding cosmic inflation helps astronomers and physicists piece together the history of the universe and offers an elegant solution to some of the most profound questions about its structure and evolution. Cosmic inflation elegantly solves two important problems in our understanding of the universe: the horizon problem and the plane problem. The horizon problem arises from the observation that regions of the universe that are far apart and have not had time to affect each other exhibit remarkably similar properties. For example, the cosmic microwave background radiation exhibits uniform temperatures over vast distances, even in regions that are causally unrelated. With global warming, all regions of the world are close together and can interact and reach thermal equilibrium. After rapid expansion, these regions extend over large distances, maintaining homogeneity even when separated by large distances. The flatness problem is related to the question of what the universe looks like in space. According to the general theory of relativity, the density of the universe determines curvature. A cold world curves inward like a circle, and a small world curves outward like a seat. Observations show that the density of the universe is very close to that required for a flat shape. Inflation suggests that in the moments after the Big Bang, exponential expansion smoothed out any initial curvature, creating a universe that appears flat. It can be compared to how a small section of a balloon looks flat, even though its entire surface is curved. As inflation stretches space, making it homogeneous and isotropic, any initial irregularities in density are smoothed out, resulting in the observed flat geometry. Moreover, inflation predicts that just after the universe began to cool and expand, the quantum fluctuations that were present during this rapid inflationary phase may have originated the large-scale structures we see in space today. These fluctuations intensified after the end of inflation, contributing to the changes in density that eventually led to the formation of galaxies and clusters. Thus, cosmic inflation not only solves the problems of horizon and flatness, but also provides a mechanism for structure formation in the universe. The implications of cosmic inflation go far beyond theoretical speculation. They help to bring together different observations and models into a coherent framework, allowing scientists to better understand the dynamics of the early universe and the fundamental principles governing its evolution. Several pieces of evidence strongly support the theory of cosmic inflation, providing a more complete understanding of the early moments of the universe. One of the most compelling pieces of evidence is the cosmic microwave background radiation, which is essentially the afterglow of the Big Bang. Detailed measurements from satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have revealed tiny fluctuations in temperature across the sky. These fluctuations are in remarkably good agreement with the predictions of inflationary models, suggesting that the density variations embedded by quantum fluctuations during inflation played a crucial role in the formation of the large-scale structures we observe today. Another important aspect of the evidence supporting inflation is the homogeneity of the cosmic microwave background. According to inflationary theory, all regions of the universe were once in close proximity to each other and may have thermally interacted. This means that temperature uniformity across vast regions of space, despite being separated by a distance sufficient to prevent light from traveling between them since the beginning of time, this explanation is consistent with the idea that these regions experienced a brief period of rapid inflation. This explanation differs from the classical Big Bang model, which does not explain the observed coherence. This theory also supports a new understanding of the macrostructure of the universe. Observations from deep space studies show that galaxies are distributed in such a way that the first small changes marked by inflation can be traced. These ancient differences in density have increased over billions of years due to gravitational attraction, leading to the formation of the craters and craters we see today. The correlation between the inflation predictions and these constructs adds another level of confidence. Finally, the detection of gravitational waves, especially from primordial sources, would be revolutionary evidence for inflation. These ripples in space-time could potentially be related to the rapid expansion of the universe during its formative period. Although these waves have not yet been definitively detected, experiments and observatories are actively searching for them in an attempt to link them to inflation and confirm the theory. As research continues and technology advances, the possibility of discovering new evidence of cosmic inflation remains a tantalizing prospect in the field of cosmology. Cosmic inflation has intriguing implications for multiverse theory, which posits that our universe is just one of potentially many universes, each with its own properties and physical laws. Since inflation describes the rapid expansion of space in the early moments of the universe, this opens up the possibility that different regions of space could be inflating at different rates or under different conditions. This suggests that while one universe may have a certain inflationary process in one universe, it may be quite different in others, resulting in a unique universe with its own set of rules and parameters. One aspect linking inflation to the multiverse is called eternal inflation. This concept suggests that inflation could occur continuously in some regions of the universe, creating pocket or bubble universes. In this scenario, while some areas stop inflating and become separate universes, other areas could continue to inflate without interruption. These bubbles could form their own universes with their own distinctive characteristics, leading to a vast number of universes, each potentially containing different physical constants, forces, and even types of matter. Multiverse theory is also consistent with the idea of inflation, providing a mechanism for the observed fine-tuning of our universe. If there are multiple universes, this increases the likelihood of a universe with the exact conditions necessary for life to emerge. In this case, the strikingly specific characteristics of our universe can be seen as a natural consequence of the vast number of possible outcomes generated by perpetual inflation. Rather than assuming that fine-tuning implies an intelligent designer, the multiverse allows for a more probabilistic interpretation in which our universe is simply one of many possible bubbles that meet the necessary criteria for the emergence of life. However, the multiverse theory remains the subject of considerable controversy in the scientific community. While inflation provides a compelling basis for understanding the origin and structure of our universe, direct evidence for the existence of other universes remains elusive. The theoretical nature of the multiverse poses difficulties in terms of empirical verification, making it a fascinating but controversial concept in modern cosmology. As research progresses, the connection between cosmic inflation and the multiverse will continue to be a fascinating avenue in our quest to understand the cosmos. The inflatonic field is a theoretical construct proposed to explain the mechanism of cosmic inflation. According to the hypothesis, this field permeates all of space and is responsible for the rapid expansion of the universe during the earliest moments of its existence. In fact, the inflation field is associated with a hypothetical particle known as the inflaton, which carries energy that can influence the dynamics of the universe. In the context of cosmic inflation, the inflaton field is central to the energy density landscape that drives the exponential growth of the universe. During inflaton dominance, the energy stored in the inflaton field behaves differently than ordinary matter and radiation. Instead of transforming into particles or releasing energy in the form of light and heat, the inflaton field maintains a high-energy state. This form of energy creates a repulsive force that effectively pulls space apart, leading to the rapid expansion characteristic of inflation. The process can be visualized as the inflaton field creating an enormous pressure that causes space itself to stretch at an astonishing rate, causing the universe to grow exponentially. As the universe expands, the inflaton field eventually begins to lose energy, transitioning from its high-energy state to a lower-energy configuration. This transition is known as superheating, during which the inflaton decays into other particles, returning matter and radiation to the universe. This process marks the end of inflation and sets the stage for the hot, dense conditions characteristic of the early universe from which stars, galaxies, and structures will eventually emerge. The exact nature of the inflationary field and its properties, including how it interacts with other fields and forces in the universe, is still the subject of intense research. Different inflation models suggest different types of inflaton fields, each with unique characteristics. The discovery of experimental evidence or observational signatures associated with the inflaton will greatly strengthen the inflationary paradigm and expand our understanding of the origin of the universe. The search for the secrets of the inflaton continues to be a key challenge in the field of cosmology, bridging theoretical physics, particle physics, and our understanding of the fundamental structure of reality. Cosmic inflation provides a compelling explanation for the uniformity of the cosmic microwave background radiation, which is the faint glow left over from the Big Bang. This background radiation is remarkably isotropic. That is, it has essentially the same temperature across the sky, with very little fluctuation. The challenge is to understand how regions of the universe now separated by vast distances could have such homogeneous conditions, especially if these regions have never been in contact since the Big Bang due to the finite speed of light. Inflationary theory proposes that shortly after the Big Bang, the universe went through a phase of rapid expansion. During this brief period, all regions of space that now appear isolated were originally close together, allowing them to exchange energy and thermal information. Inflationary expansion stretched these regions far apart at faster than the speed of light, effectively pushing them apart faster than they could affect each other. As a result, regions that are now causally disconnected were once in thermal equilibrium, creating a uniform temperature. This sudden stretching smooths out any initial irregularities in the density and temperature of the cosmic microwave background. As the universe expanded exponentially, the quantum fluctuations present during inflation became the seeds for structure to form, creating the minute variations we see today. Although inflation ensured homogeneity by allowing regions to exchange information, the resulting tiny fluctuations are important for understanding the subsequent formation of galaxies and structures in the universe. In conclusion, cosmic inflation not only explains how the universe can exhibit homogeneous conditions despite its enormous scale, but also provides a framework for understanding the tiny anisotropies that exist in the cosmic microwave background. This connection between accelerated expansion and quantum mechanics has become a cornerstone of our new understanding of the evolution of the universe, linking the state of the universe shortly after the Big Bang to the large-scale structures that can be observed today. Many models of global inflation have been proposed to explain the rapid expansion of the world. These patterns differ mainly in the underlying conditions and the shape of the climbing field. One of the first and simplest models is the new inflation model. This theory posits that the accretion point is initially in a metastable state that releases energy and initiates accretion. In this model, inflation ends when the inflaton field settles down to its minimum energy state, entering a reheating phase where energy is converted into particles and radiation. Another important approach is the chaotic inflation model, which assumes that inflation can occur over a wide range of initial conditions. In this scenario, the inflaton field can start in a high-energy state and take different shapes such as quadratic or exponential potentials, leading to inflation regardless of the initial conditions of the universe. Chaotic inflation has attracted attention due to the fact that inflation can occur in many ways, allowing for a variety of cosmic scenarios. The eternal inflation model takes this concept one step further by suggesting that inflationary expansion can continue indefinitely in certain regions of space. While some fields stop inflating and give rise to separate bubble universes, other fields continue to inflate indefinitely. This leads to the idea of a multiverse, in which there are many universes with potentially different physical constants and laws resulting from a single inflationary process. Eternal inflation paints a picture of the vast cosmic landscape, giving theorists a framework for exploring the diversity of possible universes. Another noteworthy model is the natural inflation model, which presents the idea of using axion fields, hypothetical particles that arise in theories involving strong nuclear forces, as the inflaton. This model is attractive because it links inflation to elementary particle physics, potentially bringing together different areas of cosmological research. Each of these models offers a unique understanding of the mechanics of inflation and attempts to solve different observational problems. As scientists continue to collect data from cosmic observations, such as the cosmic microwave background radiation, the ultimate goal remains to refine these models or find a single description that best reflects the behavior of the early universe. The study of different models of cosmic inflation continues to be a vibrant area of research in cosmology, contributing to our understanding of the origin and evolution of the universe. Cosmic inflation has a profound effect on our ideas about the size and age of the universe. One of the most significant consequences of inflation is that it allows a much larger and more diverse structure of the universe to exist than previously thought. Without inflation, the observable universe might be limited to regions that could interact with each other, which would pose problems for explaining the homogeneity observed in the cosmic microwave background radiation. However, the rapid exponential expansion during the inflationary period suggests that even parts of the universe that are far apart today were once close together. This understanding greatly increases the inferred size of the universe, as it implies that it may extend much farther than we can currently observe. Moreover, inflation provides a new basis for estimating the age of the universe. By studying features such as the cosmic microwave background and large-scale structures, scientists can calculate the time since the Big Bang. The increase indicates that the world grew faster than the initial conditions, so only a small fraction of the time was increased. After the inflation ended, the world continued to grow according to the laws of global expansion. This means that the age of a planet can be determined more accurately by taking into account the ascension phase and subsequent periods. Another important point concerns the interpretation of redshift in distant galaxies. Redshift, the stretching of light waves as objects move away from us, provides information about the expansion of the universe. Understanding what happened during and after inflation helps astronomers better interpret these redshifts in light of an accelerating universe. As cosmologists improve their models of both the inflationary period and the subsequent expansion, they can relate their conclusions to observed distances and the overall timescale that forms our understanding of the age of the universe. Ultimately, by viewing the universe in the context of cosmic inflation, scientists gain insight into not only how vast and old the universe is, but also how its structures have formed and evolved over time. This comprehensive understanding continues to drive research and exploration in modern cosmology. This answers some of the most fundamental questions about our place in the cosmos. Primordial gravitational waves are ripples in the fabric of space-time that arose at the earliest moments of the universe's existence, particularly during or immediately after the cosmic inflationary period. These waves are generated by the rapid expansion of the universe, which can create variations in the gravitational field. When the inflationary field drove inflation, quantum fluctuations could generate gravitational waves which, unlike electromagnetic radiation, do not interact strongly with matter. It allows them to spread freely throughout the universe, carrying information about the conditions of the early cosmos. The connection between primordial gravitational waves and inflation is fundamental to understanding the mechanisms at work in that brief but transformative epoch. In many inflationary models, it is believed that rapid expansion generates tensor modes of gravitational waves that manifest themselves as fluctuations in the curvature of spacetime. These tensor fluctuations are different from scalar fluctuations, which correspond to changes in density and are responsible for the structures in the universe that we observe today, such as galaxies and galaxy clusters. The detection of primordial gravitational waves would provide crucial evidence in favor of cosmic inflation. Their presence will provide direct observational confirmation of the inflationary model and give us insight into the energy scales that existed at the time of inflation. Scientists aim to measure these gravitational waves, in particular by observing their effect on the cosmic microwave background radiation. In particular, they will look for patterns known as B-mode polarization, which are characteristic distortions caused by the passage of gravitational waves through the early universe. Although definitive evidence for the existence of primordial gravitational waves has not yet been found, experiments conducted by the Laser Interferometer Gravitational Wave Observatory and upcoming projects such as the LIGO spacecraft and prospective missions aim to detect these elusive waves. If such waves can be detected, they would not only confirm a key aspect of inflationary theory, but would also provide insight into the fundamental physics of the universe. This includes the energy landscape and forces at work during the earliest moments of inflation. The search for primordial gravitational waves remains a tantalizing frontier in the study of cosmology and fundamental physics. Future experiments could play an important role in confirming or disproving the theory of cosmic inflation, as they will focus on several key areas of research. One of the most promising approaches involves precise measurements of the cosmic microwave background radiation. Observations with sophisticated instruments, such as the upcoming space mission known as the Simons Observatory or the CMBS-4 project. The project aims to detect tiny fluctuations and polarization patterns in the cosmic microwave background that can provide compelling evidence of inflationary processes. In particular, scientists will look for evidence of B-mode polarization, which is a signature of primordial gravitational waves generated during inflation. In addition, large-scale studies of galaxies could provide crucial insights. By mapping the distribution and motion of galaxies, astronomers can test inflationary predictions about the statistical properties of cosmic structures formed by initial fluctuations. Observatories such as the Vera C. Rubin Observatory provide a wealth of data on galaxy clusters, allowing scientists to compare these observations with theoretical predictions of inflation models. Differences between observed structures and those predicted by inflation can provide important information about the validity of the theory. Searching for long wavelengths is one of the most accurate methods of checking for inflation. Missions such as the Space Laser Interferometer Antenna are carried out to detect electromagnetic waves propagating in space. By measuring the stretching and compression of spacetime caused by these waves, scientists will be able to obtain conclusive evidence of the conditions that existed during the inflation. The detection of such waves would not only validate inflation, but also provide insight into energy scales, potentially opening up new physics. Moreover, advances in particle physics and high-energy experiments can provide indirect evidence of inflation. For example, results from particle gas pedals such as the Large Hadron Collider can help identify candidates for the inflaton field by revealing connections between particle physics, symmetries of fundamental interactions, and field theories that are consistent with inflationary models. The discovery of new particles or interactions could ultimately support or disprove the existing inflationary framework. Future experiments will shed light on our understanding of global inflation. With detailed observations of the microwave background, superstructures, barrier waves, and advances in elementary particle physics, scientists continue to test the predictions and implications of inflation. The search for real evidence is an interesting avenue in astronomy to deepen our understanding of the origin of the universe and its underlying processes.